Module 2, Lesson 2 covers logic bit operations. For this module, we'll be covering logic bits, the different bitwise operations you can perform on your logic bits, the different logic gates that these corresponding operations represent, and the different hardwares or logic ICs that actually use to implement these different logic gates, as well as their datasheet. A bit or a binary digit can be used to represent the truth value. A bit value of 1 is used to represent the value of true, and a bit value of 0 to represent the value of false. Therefore, a propositional letter or a Boolean variable is either a value of 1 or 0. Computer information is often represented using bit strings, which are sequences of ones and zeros. Any particular data, information, or even process is actually represented using a set of bit strings. Computer bit operations eventually correspond to the implementation of your logical connectives in bit strings. The output is obtained from the logical truth tables of operators like OR, AND, XOR, etc., etc., for the different corresponding bit operations. Bit operation on strings can only be performed on bit strings having the same length. The length of a string corresponds to the number of bits in your given string. Hence, bit operations are applied only to strings with equal number of bits and is applied to bits of the same position. So, its result is also a bit string of the same length. The same propositional connective symbols are used in bit operations like AND, OR, XOR, etc., etc., which are represented as bitwise operations. This is one such example. Let's say we have the following bit strings A and bit strings B. Both are correspondingly 10 bits long. In order to perform a bitwise NOT operation from, let's say, A, bitwise A, therefore, your complement of A or A naught would eventually mean inverting all your corresponding bit values from 0 to 1 and all ones to 0, starting, of course, with your corresponding least significant bit, which is found here on your corresponding bit strings, all the way up to your most significant bit, which is this bit, on your corresponding bit string. Hence, you'd end up now with a corresponding complement value for your bit string A to be equivalent to this respective bit string. Likewise, you could perform that on your bit string B, therefore the complement of your bit string B would now end up with this respective bit string. You could also perform different bitwise operations noted there, like the bitwise AND. In applying then the bitwise AND operation as mentioned, you simply need to evaluate the corresponding bit operation using your logical truth table for your AND operator and compare that with bits of the same position, starting again with the least significant bit all the way to your most significant bit. So if we apply them on bit strings A and B, therefore you'd end up with a corresponding bitwise AND result, which is equivalent to this bit string. You could also perform a bitwise OR on the following bit strings, let's say with the following bit strings A and B. Therefore, your respective bitwise OR result would eventually have this given bit string. You could also perform a bitwise XOR, given up by our corresponding symbol here, for our bit strings A and B. Hence, our bitwise XOR result would now be like this. You could also do bitwise implication. That is, in this given expression, your A happens to be your hypothesis, and your B represents your corresponding conclusion. Therefore, with bit strings A and B, your bitwise implication would then eventually have this corresponding result. Likewise, you could also do a bitwise biconditional for the following bit strings, which should eventually end up with a bitwise biconditional result equal to this bit string. The following corresponding bitwise operations are actually implemented and performed by your hardware using what you call a logic gate. A logic gate basically is a particular device that implements your given particular connective in order to implement operations on your propositional logic. In describing then circuits for your propositional logic, you often use these corresponding logic gates and combine them, ending up with what you call a combinational circuit or combinational network. The following basic logic gates are as follows. So you have the NOT gate, which eventually represents your negation connective. And on this particular logic gate, the left terminal would be the input for your proposition, and then the right terminal would be the output for your corresponding proposition. Hence, if I input a value of true, on the output side, it becomes false. Or if I input a value of 0, on the output side, it will display a value of 1. You also have the AND gate for your conjunction connective, whereby your input side on the left contains 2 terminals, noted for your P and Q. So again, if this shows you the inputs for your propositional letters, the output would be on the right side, would eventually give you this expression. You also have the OR gate. Again, the inputs are on the left for your propositions. Thus, on the right side, you'd end up with the expression P or Q. And finally, you have the XOR gate, or the exclusive OR gate, and the inputs would be on the left-hand side again, and your output would be this given expression, seen on the right side. There are other gates that are referred to as the universal logic gates. A universal logic gate, like a NOR, simply combines your corresponding gates, or, and the output is inverted. So on the left-hand side, you have inputs for your propositions P and Q, and on your right-hand side, you'd end up with this expression. As shown on the expression, it's like a combination of an OR gate whose output is inverted. If we then define this using a corresponding truth value, then your truth table will eventually end up like this, along with your logical truth table like this. The other universal logic gates are the NAND gate. A NAND gate again has inputs on the left for your corresponding propositional letters, and the output would be this corresponding expression, which is, if you look at it, it's like a combination of an AND gate whose output is inverted. Thus, the truth table defining your NAND gate would look like this, whereby the outcome now would be the inverse of your corresponding conjunction connective. There, your logical truth table would now appear like this. And finally, your XNOR gate, which is, again, on the left-hand side would be your inputs for your proposition letters, and then you'd end up with an expression on the right-hand side to look like this, which appears to be a combination of an XOR gate whose output is inverted. Therefore, since we already know how an XOR gate operates, we simply invert that outcome and we end up with the outcome for your XNOR gate. So seen here, you have the truth table defining your XNOR gate and its logical truth table. In return, you could also perform them in your bitwise operations, since they are defined also using a logical truth table. Therefore, you could perform the NOR, bitwise NOR, for your bit strings A and B, ending up with this corresponding bitwise NOR result. Likewise, you could perform a bitwise NAND for your example bit strings A and B, ending up with a bitwise NAND result to be equal to this bit string. And finally, you could also perform a bitwise XNOR, which eventually results into this given value. When implemented, these particular logic gates appear like integrated circuits. So a corresponding logic gate IC of a NOT gate eventually is referred to as a 7404, noted to be a transistor-to-transistor logic gate. This corresponding logic gate, as defined, physically looks like this, whereby the labels of your 7404 are actually labeled on top, allowing you to distinguish that this particular IC is for your NOT gate. Likewise, there are pin configurations on your corresponding ICs that allows you to identify which pin corresponds to your input and which pin corresponds to your output of a given particular gate. As noted, these particular ICs will not work unless you supply them with power. Therefore, pin 14 normally is dedicated for your 5-volt DC supply, while pin 7 is often dedicated for your ground. You also have the logic gate for an AND gate, which is called the 7408. Again, it appears similar to your 7404. However, this time, this particular logic gate implements what you call your conjunction connective. And as seen from this corresponding schematic, you could identify the corresponding pins again for your inputs and your outputs. And naturally, again, pin 14 is dedicated for your VCC, while pin 7 is for your ground. This now is for your OR gate, which is a 7432. Again, if you do look at the actual IC, it appears similar to your corresponding 7404 and 7408, except this time, this is numbered as 7432. And likewise, you could see the inputs and output of this corresponding logic gate. For your XOR gate, it's actually referred to as a 7486, which again, eventually looks like this. So a 7486 eventually implements an XOR gate, and as seen there, your pins 1 and 2, again, are dedicated for inputs, while your pin 3 is dedicated for your output for your first XOR gate, while pin 14 and pin 7 is still dedicated for your VCC and ground respectively. For your NOR gate, which is a 7402, this time it has this corresponding pin configuration for your corresponding 7402, which eventually, if you look at the physical appearance, looks like your previous ICs. So all of them note corresponds to a 14-pin IC. And as mentioned, pin 14 is dedicated for your VCC, and pin 7 is dedicated for your ground. This particular IC now implements your NOR gate. And as seen here, your pin 1 now is the output, while your pins 2 and 3 corresponds to your input. And then you have the IC for your NAND gate, which is 7400. And as seen from this corresponding NAND gate, again, if you look at the actual physical appearance of your NAND gate, it looks like your previous ICs. And again, pin 14 and pin 7 is dedicated for your VCC and your ground. Here, pins 1 and 2 again are for inputs, while pin 3 is dedicated for an output for your first NAND gate. And then you have the XNOR gate, which is the 74266, given off to be with this pin configuration, and appears to be like this. So much like the previous ICs, pins 1 and 2 are dedicated for the first inputs of your first XNOR gate, while pin 3 is the output for your first XNOR gate. This particular information is often seen on what you call a data sheet. A data sheet basically, or a specification sheet, is a documentation that summarizes the performance and other characteristics of your given particular ICs. This particular information is often used when creating a design or using your particular ICs. Typically, a datasheet is created by your manufacturer. It begins with an introductory page describing the rest of the document, following a list of specific characteristics with further information on connectivity of your devices. In cases where there is relevant source code to include, it is usually attached at the near end of the document or separated into another file. Datasheets are created, stored, and distributed via product information management or product data management systems. Depending on the specific purpose, a datasheet may offer an average value or a typical value or a range of values, whereby engineering tolerances or nominal values are often applied. So a datasheet usually is used for commercial or technical communication to describe characteristics of your given item or product. And it is published by your manufacturer. So technical specifications of your particular device or material or product or service is actually seen there. This is one such example of your datasheet whereby I've shown here the datasheet for a 7400, which is a NAND gate, showing you that there are three corresponding packaging for your NAND gate as seen on the code. So you have the DM74LS00M, which is a 14 lead small outline integrated IC. You have the DM74LS00SJ, which is a small outline package, and the DM74LS00N, which is a 14 lead dual inline package, which is the most common one, no? You've seen on the picture or the image. It also contains your corresponding connection diagram, which eventually shows us the pin configurations of your ICs. Likewise, your respective truth table, how this particular logic gate operates. It also includes different ratings of values that are tolerable on your respective ICs. Meaning if you go beyond these values and connect your ICs on different conditions, in some cases, your IC may burn out. There are electrical characteristics there regarding your ICs, which shows you how many inputs can be connected all at the same time, and what would be the corresponding rating of currents circulating in your ICs the moment you connect these devices. Likewise, you also have switching characteristics, which allows you to show how fast your corresponding transistor to transistor logic operates the moment input values change instantaneously. And finally, you have physical dimensions included there, which allows you to insert your corresponding ICs on particular PCBs, shaping them and fitting them exactly on your corresponding host so that they would fit promptly on your respective devices. Likewise, you could also get cartridges whereby you simply insert this particular device and then solder them into your corresponding boards. So all of these are included within your data sheet. This ends correspondingly your Module 2, Lesson 2, whereby we've covered your different ICs, the different connectives that are eventually implemented by your logic gate ICs, the corresponding characteristics of your logic gate ICs and their truth tables,